Now, do you see some notes, electromagnetic induction?
Yep.
Yes?
Yeah.
Okay. Okay, thank you. That's great. Okay, so we will start the meeting. So good afternoon, and thank you for joining in, Gus. Now, this was the lesson. Electromagnetic induction was the lesson last week on Friday, but I thought I will explain it a little bit more, or just some key points in the electromagnetic induction. So. Uh, one or two lessons before where we did what we call as a motor effect. So we will look at the diagram first. So so in this one, there is a rod and it is only connected to a resistor. So there's no battery, so there's no current flowing in the circuit. Now, if this and this is made up of some conducting material. Conducting material means like copper or iron or something, and they have got electrons which are free to move from atom to atom. So when this rod is moved downwards, there's a magnetic field. As it moves down, it cuts the lines of magnetic field. And due to that cutting of the lines of magnetic field, electrons in this rod AB, they experience a force and they move to one direction. And if they're moving in one direction, either this way or that way, and if it's a complete circuit, that means current is flowing. So this current or this voltage that is induced across AB, because it doesn't come from a battery, so it is called induced voltage. And this induced voltage is proportional to the magnetic fields. If magnetic field is stronger, there will be larger voltage induced, or if the speed is faster, or third thing is if the length is, bigger length is placed in the magnetic field. So like in the diagram, it's only this much part from here to there, which is placed in the magnetic field. So electrons only in this area will be experiencing a force. So what we say is that voltage induced is equal to BVL. B is the magnetic field, V is the speed of the rod, AB, L is the length. Now sine theta refers to the angle between the motion of the rod and the magnetic field. So if you look over here in this one, magnetic field is going from north to south to the right of the page. This one is moving like down the page. So they're at 90 degrees angle. So there will be maximum voltage induced. However, if rod was held like parallel over here in this direction and then move downwards, then it will not cut the lines of magnetic field. It will just slide between the lines. Okay, so then there will be no voltage induced, or it will be zero. At another angle, it will be somewhere in between. But generally, you don't have to worry, because you will be given the questions where motion and magnetic field, they will be at 90 degrees angle. So if there is a voltage induced across AB, there will be a current, and that current is called I induced. And if there is a resistance R in the circuit, then I induced is equal to V induced over R. Now this one, so this is called generator effect. That means motion and magnetic field together, they're producing induced voltage or induced current. Now it's different from the motor effect that we did last time. So in the motor effect, what we do is that it is the current carrying wire. So the current and magnetic field together, they make the wire move. Okay, so this one is different. But the rule that we find to use the direction of the induced voltage is same. So if we look at the what is the rule? It's called the right-hand generator rule. So what's different in this one is that in the previous one, motor rule, this one was the direction of the current. Okay, fingers were the direction of the magnetic field, so that's the same. But this time, instead of current, it is the motion. Okay, so your thumb has to be pointing in the direction of the motion, fingers in the direction of the magnetic field. So the palm, in this direction, your palm will move, or you can put your fingers at 90 degrees angle like that. That will give you the direction of the induced voltage. So let's apply this rule to this diagram over here. So what I would like you to do is, if you could use your right hand, and if you could point, so your thumb is pointing down the page or down the screen, so you can have your hand against the screen. So thumb is pointing down the screen. Now, if you turn your right hand so that your fingers are pointing to the right of the page, so you might have to twist your body or your screen somehow. Now, so your thumb is pointing down the page, your fingers are pointing to the right of the page from north to south. So if you now move your hand, or like if you are moving your palm or giving someone a slap with your right hand, can someone tell me what direction does your palm move? Does it move from B to A or A to B? So thumb should be pointing down in this direction. Fingers are in that direction. So if you do it, then your palm is coming towards you. Okay, so if you move your right hand, the palm is coming towards you. So that means induced voltage and induced current is from B to A because it's coming towards you. That's the third dimension, which is hard to show, but it is from B to A. What it means is that current in this part of the wire or rod will be flowing from B to A. Now, because it is a complete circuit, so current will be going in anti-clockwise direction. Just imagine if this was not there, these connections were not there, and it was only rod BA. So there will be current will not be flowing, but nonetheless, voltage will still be induced. And so voltage will be induced. So inside this wire, if current is moved this way, and current is made up of conventional charges, so that means electrons would have moved in an opposite direction to the conventional current. So conventional current, we figured out, is in this way, anti-clockwise. So electrons would have moved that way. So if electrons move that way, that means this end is negative and this end is positive. What it means is if these wires were not there, then this rod, while it is moving, it is acting like a little battery, okay, where this end is becoming positive and this end is becoming negative. And if there's a complete circuit, then current will come out of the positive into the negative. Now, all of this one only happens while the rod is moving. If the rod is stationary, then there will be no induced voltage. Is everyone following so far?
Yeah.
Okay. Now
Yeah.
I want to show you an animation which is like this one. So now this one is a straight wire which is moved in a magnetic field. Now instead of moving the wire, we can move the magnetic field by moving these two magnets up and down, okay, like that. So as long as there is a relative motion between the magnetic field and the rod, voltage will be induced because lines of magnetic field will be cutting this rod and pushing the electrons in one direction, hence voltage is induced. But voltage can be also induced if the setup is like this one. Okay, do you see a little bit newer screen, a new part of the?
Yeah.
Okay, so this one is like a copper wire. This is like a solenoid which has been wound like a solenoid. And this one, so there is no battery here. This one is just a galvanometer or a meter that moves either in this direction or that direction, depending on the movement of the magnet. So in this one, if a magnet is moved towards this coil, then remember, the magnet has got a magnetic field like shown in this diagram over here or there. So when the magnet is moving here, then lines of magnetic field will be cutting these wires or this wire. This is a similar diagram as that one. Therefore, electrons in this one will be experiencing a force and they will move. And if they move, that means voltage or current is induced, which can be indicated by this movement in the needle or the movement in the needle over here. I'm going to show you an animation. Just give me a second until I load up my
Miss, you're muted.
Thank you. Do you hear me now?
Yeah.
Okay. Somehow, when I went to that particular screen, it kind of put me out of the meeting. So that's why I had to re-enter it again. So I will try one more time. But if it doesn't happen, then what you can do is you will have to try this animation on your own. But I will just try one more time. So I will have to share the screen again. Now, okay. Because I don't know, there is some technical problems. It's not letting me open the animation, but so I will stop trying it. But the link is given in the notes, so if you can go and try that one on your own. Is that all right?
Yeah.
Okay. What I can do is later on I will kind of make a little video on this, what I was going to explain in the animation, and post it in your Google Classroom so you can watch it there. So that was all for the electromagnetic induction. So remember, electromagnetic induction is different from when there is a force on a current carrying wire. So that was all. So we had completed the whole topic. And now, if you have already might have noticed in Google Classroom, so today's lesson is completing your 2 assignments, and then completing those assignments and submitting it on, in Google Classroom. And so we have 4 lessons this week, and you know that until we go into level 2, schools will not open. So we will just assume that we will be online for rest of this week. So For the next 3 lessons, I will be posting some revision work. And I thought that you've been doing electricity and electromagnetism for like last 4 or 5 weeks. So we will just change the kind of a topic a little bit. So I will post some revision kind of past papers or past papers questions from past papers in Google Classroom. So and that will be on mechanics topic. So if you could do those kind of revision questions for rest of this week, and I might put a little kind of a assignment on mechanics so that you can revise it, complete that assignment, and submit it on Friday. Because we're coming close towards the end of the year, and so we need to kind of have started some revision. So that's my kind of program for this week. Any questions, girls?
No.
Everything is good?
Yeah.
Okay. So thank you for joining in again. It's good to see a good turnout. So have a nice week and just keep up with your work. And if there is any question or query, just send me an email and I will try to answer your queries. Okay?
Thank you.
Okay.
Thank you.
Thank you.
Bye-bye.